Hello and welcome to the Scan-Xpress webinar on 3D inspection. Today we will be discussing the inspection software GOM Inspect suite. We will talk about the basic and advanced inspection workflows, the benefits of using a fully parametric software, and the functionality within the free GOM Inspect. We will have a Q&A session at the end, so please use the chat window to ask any question. Let me introduce you to our experienced and knowledgeable team.
Firstly, a big thank you to the team that have worked so hard to put this webinar together. In my top left, Rajiv, Aman, Josh, Benjamin, and Olivia. Thank you guys. I hope you enjoyed the presentation.
Scan-Xpress are the GOM distributors for Australia and New Zealand. We also offer access to our technologies and expertise through the provision of bureau services. We are a completely mobile service. We can come to you anywhere in Australia or overseas if needed. As Australia's manufacturing heads into a new era of expansion, so are we adding representation in new geographies. With our headquarters in Melbourne, we have recently added representatives in New South Wales and Queensland. More soon to come. GOM have emerged as the market leader in optical scanning and inspection software. The GOM ATOS scan boxes are the systems of choice within manufacturing industries across the globe, providing fast and accurate inspection. The recent advances in GOM technology have led to the release of the ATOS Cube. This is an entry-level optical scanning system which can capture superior data on a large range of parts. GOM's inspection software is considered the best in class for usability and functionality.
GOM Inspect can be an inspection tool for all metrology systems, not just GOM scanning systems. Any STL data, STEP, IGS, or point data can be imported and inspected in the free version of the GOM Inspection Suite. The professional version of the software can also accept native CAD formats such as SolidWorks, Siebens, NX, and CATIA. The free version of GOM Inspect is a complete inspection package, although some of the advanced inspection functions are only available in the professional version of the software. We will talk about this in more detail later in the webinar.
Today we will be hearing from some of the team here at Scan-Xpress, Olivia, Josh, Ben, as well as myself, Kevin. We will be taking you through some of the key workflows and functionalities of the software. Live application examples will be used to showcase the software's strengths as well as illustrate its speeds of use. Starting with a brief introduction to the user interface and some simple inspection workflows, we will then delve into GD&T and template-based inspection, before finally looking at multi-part inspection and even multi-stage inspection. We hope you enjoy. To start the introduction to the software, Ben will run us through the Start menu, where you can start new projects or continue working on existing projects. You'll also see how you can access sample data and offline training materials. Ben will also explain how to navigate the 3D view. Over to you, Ben.
For these examples, we're going to use the free version of GOM Inspect Suite. Now, we'll be able to tell the difference between the free version and the professional version of the software by looking for the icons on the left-hand side. The free version of GOM Inspect, which you can see on the left screen here, has the three icons available, which is the inspection, the reporting, and the mesh editing. The professional aligned version, which is on the right-hand side, has some of the more advanced data capture features, such as digitize, where we capture the scan data using the GOM optical scanning systems. We'll explain a bit more about the differences between the free version of GOM Inspect Suite and the professional version a little bit later on in the presentation. This is the start screen for GOM Inspect Suite. Here we can open a new project, open an existing project, or download some sample data from GOM. The Get Started Guide is an offline training for showing some key workflows for the inspection and data capture. Now I'm just going to open a recently used project. So now we go into the software. This is our live 3D view. And what we can do is see the part in the center. We can move it around using our mouse controls. We can zoom, we can pan. We can also snap to different directions using the cube in the bottom left-hand corner. The Explorer view on the left-hand side has all of the key features that we've created for this part. And what we can do is click and drag from the Explorer view into the 3D view to show that element exclusively. We can also hold Shift and add that to the 3D view by clicking and dragging, or if we hold the right mouse button and drag in, then we can choose between showing it exclusively or adding it to the 3D view. The tabs on the far left-hand side are the different modules in the software, the different modes of operation. Here we've got inspection. Here we can look at our report pages and all of our created report pages, and we've got mesh editing down the bottom. And as we flick between these modes, the icons on the top bar change, which are our key access to the key features for those modes in the software. Now the 3D view can be adapted and configured to your exact requirements. So all of the features can be clicked and dragged to have it as a separate window, or we can add them to any of the other tabs or any of the other windows we like. This can also be used on a multi-screen, where we can drag some of these views out onto a secondary screen to help us analyze our data and do our inspection. To reset the view, we just go to View here, Screen Setup, and reset all workspaces.
Thank you, Ben. In this next section, Ben will continue by taking a closer look at some simple inspection workflows. He will illustrate how to import data, perform some initial alignments such as global best fit, create deviation color maps, as well as extract some dimensional comparisons. Once an initial general understanding of the part's condition has been achieved, Ben will showcase how to perform further alignments based on features and drawing datums. This can include multiple alignments held within a hierarchy, each capable of having their own report pages within the one report.
Importing data into GOM Inspect Suite is nice and simple. All we need to do is click and drag into the 3D view any files we want to import. So in this case, I'm just going to import an STL. So the free version of GOM Inspect Suite can accept STL files as well as point cloud data and CAD files in STEP or IGES format. If we work in the professional version of GOM Inspect Suite, then we can accept native CAD files such as Parasolid or CATIA, Siemens NX, SolidWorks, as well as PMI data. So again, we just click and drag in our STEP file here, and we're going to add that to the part. So to export the data, we just click on the data we want to export, in this case the STL. We go to File, Export, Mesh, and STL.
As well as all the features, geometry, and report pages, the GOM Inspect software holds all the measurement information associated with the capture of that part. Under the Measurements tab in the Explorer view, we can access all the individual measurements used to capture this part, in this case using the Atos queue. By pressing Tab, we can bring up the information panel on the right hand side. This shows us the system used and the associated measuring volumes, as well as all the quality parameters. So here we can see the transformation deviation, any movement during the measurement, or lighting change. This goes for the measurement series as a whole, which can be accessed right here. All images taken during the measurement process are also available. This can be accessed down here using the image mapping icon. This brings up the images associated with each particular measurement. We can use this to check serial numbers or interrogate how a part was positioned during measurement.
Here we're going to look at a simple inspection workflow in GOM Inspect. First, I'm going to import the scan data, in this case an STL file. This part was captured using our GOM Atos queue, but any STL file from any scan data can be imported and inspected using GOM Inspect Suite. So now that file is imported, it's created in the tree on the left hand side. We can view the scan data here, and by opening up our menu on the right hand side, we can view the mesh structure and see the high quality, high resolution mesh that we can create using the Atos queue. I'll import my CAD model, in this case it's in a step format, and add it to the part. So now this has been imported, you can see the CAD model sitting in the tree on the left hand side. So the first thing we'll need to do is to align the part. So the initial alignment, in this case we'll use a pre-alignment. This is just going to be a global best fit, just to get the two parts close together. So now that's complete, we can start our inspection. So surface comparison on actual is usually a nice place to start. This is going to show us a color map deviation from the scan data to the CAD model. This is a great visual way to be able to inspect our part. We can adjust the legend on the right hand side here, and we'll be able to see nice and clearly any parts that are in or out of tolerance. Now obviously this is just based on the best fit at the moment, so this is more giving us an idea of making sure that all the features have been machined correctly and there's no large deviations from this part to the scan data to the CAD model. We can also apply a tolerance based legend to show us any features that are in or out of tolerance. Creating geometries in GOM Inspect is done using the construct menu, and we can create a cylinder here, and by holding down control and clicking on our CAD model, that will create our feature here. Once those features are created, we then apply a measuring principle, in this case a fitting element, to fit this to the scan data. We can adjust our filtering method, and we've got some advanced features that we can use here. But once that's done, we can now inspect these features. So this icon, the eye inspect, is toggled on the top bar, and this controls the measuring principles as well as the dimensional checks and the GD&T. And this updates depending on what I've got selected. So for example, we've got two cylinders based here. We can inspect those, and it gives me the option of radius or diameter, everything that's relevant to a cylinder. We can adjust our tolerances here and adjust our nominals if necessary here. So now that inspection's done, we can create our report pages using the camera icon, or export this as a tabulated form as a CSV file right here. But let's go a bit further. We want to create a geometrical alignment on this, something that's going to be consistent for our further workflow. So I'm just going to create some more features. So just two more cylinders right here. And then some planes. So now with these new features, I'll apply my fitting element measuring principle to convert those to scan data. And now we'll create some intersection points between the cylinders and the planes. For these, we'll use the measuring principle reference construction to follow on the scan data the steps that we created them using on the CAD model. So I'll select those 4 points here, go to the alignments, and we'll use the RPS alignment, the reference point system. We'll add in our 4 points here and create that alignment. Now this has added a new alignment in my alignments tree. So we've got our initial alignment, which is that global best fit, and our new alignment, which is based on these mounting holes. Now of course we can inspect those mounting holes by selecting them here. Our eye inspect, go to our dimensional checks, and that is changed, updated for whatever is relevant to the feature I've got selected. So we can inspect these in X, Y, and Z. And we can flick between the two alignments, and we can see the deviations adjusting depending on which alignments we've got selected. And this goes for the color surface, the surface deviation as well. We're here. So here, this is updated for the RPS alignment, and you can see it's shifted the deviation away from the mounting hole where we're aligning to the CAD model. If we flip back to our pre-alignment, our global best fit, this should even out the deviation across the whole part. And that's updated there. So again, these report pages can be created using the camera icon, and we can create a report page in the first alignment, update this to the RPS, we'll create a new report page in the RPS alignment, and we can see that the relevant alignment is down in the bottom left hand corner. Now if we go into our Reports page tab, we can then flick between these two alignments and these two report pages.
Thank you, Ben. Ben just showed us how easy it is to create color plot deviations and how the software can quickly produce dimensional inspections. Now we're going to delve into some more advanced inspection capabilities and look at how the software performs GD&T inspection. The combination of the powerful reporting and inspection modules provides the ability to not only replicate a CMM report, but gain an even deeper understanding of your part. The benefit of having full field of view data means we are not limited to single-digit GD&T values. We can look even deeper at the effect of thousands of points that describe the feature and understand the influence of all characteristics on the component's functionality.
Creating GD&T inspection in GOM Inspect is as easy as creating dimensional checks. So here we've got a plastic injection molded part. Again, we've got the CAD model here shown in blue and the scan data in grey. I've also got the drawing associated with this part, which is right here. So here we can have a look at some of the inspection and create some of these GD&T features. So the first feature I'm going to create is a flatness check on this area, this planar area here. So again, we go to the construct and create our plane on this surface here. Just as before, we create a fitting element as a measuring principle to convert that to the scan data, and then we can check using our GD&T feature on our Inspect. So here we'll apply our flatness check, and we'll check the drawing with our tolerance, which in this case is 0.1 of a mil. So apply our tolerance here, and this gives out our flatness check. Now another thing we can do is potentially switch our labels to an ISO style label. We'll just switch the annotation plane and the reading plane here. So then what we can do is actually mirror our manufacturer drawing and get a nice inspection report that our shop floor operators are going to really be able to get a good understanding from, because it mirrors the same layout as our manufacturer drawing. Now another thing we can do in the GOM system is get a deeper understanding of our GD&T features by using color deviation representation. So we flick that on the right hand side right here, and what this gives us is a color map deviation of that flatness check. So rather than just getting our one figure dimension answer, what we can actually do is inspect every single captured point on that surface and how that is affected by that flatness check. So this also works on other features. So I've created a section right here on this small cutout. So for this, the inspection requirement is for a line profile. So again, I've selected my section. My GD&T is updated for everything that's relevant to this feature. So in this case, we'll select line profile. I'll select my datum system, which I've created from the drop down, and we'll apply our tolerance, which in this case is 0.25 of a mil. So this gives us our one figure answer. So again, we've got our inspection report to show that it's good and the part passes this feature. What we can do is click on our GD&T check and do the show color deviation representation. What we can then do is maybe increase our vector scaling to make this a bit more obvious. We can also apply some deviation labels. Apply our transparency again so we can get a good understanding of exactly of the whole way around this check, and create our report page. So using these figures, we can replicate our inspection report or replicate our CMM report, follow the exact same principles, create our datum systems, create all of our GD&T checks. We can also use this color deviation representation to get a full understanding of the part, not just that single digit answer.
Thanks once again, Ben. In this next section, Josh will illustrate the tremendous saving in time that's possible when using the professional license of GOM Inspect and the functionality of template inspection. Perhaps just a few key inspection features are required. The part is scanned once and a template created once for all the required elements. In future, all inspection becomes a one-button operation. New scan data sets are simply dragged and dropped into the template and updated instantaneously. Reports are immediately generated and formatted to suit the user. Data capture in minutes, inspection in seconds.
I'm going to quickly go through the workflow in GOM Inspect suite when we are using a prepared template. This is a feature of the Professional module. From the home screen, we can access the inspection templates here. Here we have an inspection template for an 8mm screw that I previously prepared. I have created all of my inspection elements before any data has been captured on the CAD model. There are only 3 elements that I'm interested in: the overall length, the thread diameter, and the screw head angle. All I need to do now is load in my scan data. This screw was scanned at 17 micron resolution on our ATOS compact scan. The software will automatically update, providing me the completed report. Now that the project has updated, we can go into the report module to look at the completed report. We can see here the title page, the tabulated results, the thread diameter with a deviation of 0.5 micron, the screw head angle, and the length check. We can see that all 3 checks are within our tolerances. We can now export our report page as a PDF file and the tabulated results as a CSV file.
Thanks Josh for the explanation of the inspection templates. Now we're going back to Ben, who will be working with the scan data from a plastic injection mold tool. This tool produces the part that we saw when Ben went through GD&T inspection earlier. This time, however, we're going to be looking at inspecting assemblies and how the software can inspect not only back to the CAD models, but can be used for inter-part inspection, including distances between mating faces.
This is a parts project, so this is how we do our multi-part assemblies. So as you can see in the Explorer view, it's segmented into the different areas for the different parts. So we've got the scan data for the top half of this mold tool. We can see it here with the associating CAD model. The same with the bottom half and the CAD model here, and then there's a side core inside here. So what we can do with this is we can do separate alignments for each of these parts of this project, as well as alignments for them together. So if we have a look at the surface comparison here, again we just click and drag that to bring that in, so we can have a look at this as a tolerance legend for the surface comparison on the lower half of the tool. So this is comparing the scan data back to the CAD model and identifying if it's in or out of tolerance. Maybe we can change this to a more standard tolerance. And then we can see any areas of wear, any areas that are outside of our specified tolerance zone here. We can also inspect every area on this surface by using our deviation labels up here. So now with the alignments, we've got alignments separate for each of these cores, so we can see here. So we've got a best fit associated with this bottom half, same as a pre-alignment for the side core, and we've got a geometrical alignment for the top half. So if we look at the scan data from that top half, what we can do is select the alignment, and then down the bottom of the Explorer view we've got this Relate To tab. Now what this does is this is going to show us all the features that relate to that alignment. Now what we can also do is do the Edit Creation Parameters, or press the F4 button. This brings up the window that was used to create this alignment initially. Now we can view this and we can see what was used to create this alignment and the hierarchy involved. What we can't do is actually edit that alignment. That's something that's locked behind the Professional module. So if we wanted to change anything here, we need to delete that alignment and remake it. If we had the Professional version of the software, then we could just change any of these features, switch around the hierarchies, and everything would update from there. So what we can do is then bring these features into the 3D view and assess how these features were created and what they are used for in this alignment. So again, we select this plane here, what we can do is press the restore point selection, and that's going to highlight the areas on the CAD model that we used to create that plane. And if we deselect that and select the plane and the scan data, again we can restore point selection and look at the areas on the scan data that we used to create that data plane. The other thing we can do is also do the edit creation parameters for this plane and look at what fitting elements we used to create this plane. So in this case it's a Gaussian 3 sigma fit. Again, in the professional version of the software we'd be able to change this and everything would update, but seeing as we're in the free version of GOM Inspect Suite, what we can do is assess it, identify what our inspectors used to create this, but if we wanted to make any changes we'd need to delete it and remake that feature. So with the inspection, one thing we can do from here is actually look at the mating of these two parts of the model tool here. So I've created some tags which you can see in the Explorer view down here, and if we look at the ceiling faces here, so this is a section we've taken from the top half of the mold and the bottom half of the mold, and we can look at the deviation and the distance between those two faces. But seeing as we've captured the full surface detail, we can also do that as a 3D color map. So this is a color map showing the distance between those two ceiling faces. From here we'll be able to identify any wear, anything that's going to cause issues on our part going forward. So here we're just going to use the inspection features within GOM Inspect to really analyze our part and get a good understanding of what's going on with our component here. So again, we're working with this multi-part tool and we've got the surface comparison. So this surface comparison is just checking that closest point from the scan data to the closest point on a CAD model and coming up with this color map. And what we can see here is straight away the areas that are outside of the set tolerance that we've applied. So what we can do is adjust that color map to get us a better understanding of exactly what's going on with this part. So let's reduce this tolerance zone here, and what we can start to see is the actual cutter marks from the tool appearing on the tool surface. Now one of the reasons we can see this is because we're working with extremely high resolution scan data, and we can see that if we look at the scan data right here with the mesh structure. So not only can we see those cutter marks, but we can now inspect them and know what effect they're having on our tool surface. The other thing that we can look at is any transitions between the different color bands. So what I mean is something like this, where we're looking at a nice green surface here, where it's transitioning to high. So anything orange or red means that the scan data is sitting above the CAD model. Anything blue means the scan data is sitting below the CAD model. So here we can see this transition here. If we look at the CAD model, that should be all one surface. And if we look back at the surface comparison, the rest of this surface is all pretty good. There's no big transitions. So there's obviously something going on there. So if we look at the mesh structure again, and because we've got this high resolution mesh, and we can see as the cutter mark, and obviously the cutter mark has just missed this small pocket. So one of the passes has just missed this small pocket, which is why we can see this transition. And what we can do is use deviation labels to assess what that transition is. So we're talking about 20 microns across that surface. But by using these color maps, it becomes really obvious where these features are. So another example on this top side of the surface. So let's look here and our color map. So again, we're just going to switch to an 8 color gradient. I quite like this 8 colors because it has this step in, and it makes it really clear where it's going in from one boundary to the next. So let's move this down to something reasonable. And what we can see is, straight away we've got this really red area right here. So let's see what's going on with that. So we can bring up our CAD model. You can see that this pocket should have a radius at the bottom. And if we overlay our scan data, see it's just not there. It's got a flat. So we use our color map again, bring up some deviation labels and see how big that is. 1.3 mils, pretty considerable. The other thing we can do is use our clipping plane to just clip a section straight through here. And what we can do is overlay our color map with our CAD model. Then we can see exactly where that deviation is. Again, deviation labels will help with this.
Thanks, Ben. One of the really nice and relatively recent developments in the software is the capability to inspect multiple data sets of the same part as it undergoes different processes within its production cycle. In this example, Ben will showcase an additively manufactured part and examine the influences removing the support structures has on the final geometry. We will then explore some statistical analysis within the trend functionality. Additionally, we will showcase how a repeatability study can be used to quantify the accuracies possible with a top-of-the-line GOM ATOS 5 sensor. Truly impressive for a non-contact system.
Inspecting between multiple parts is a common feature in metrology. This can be used for statistical process control, measurement systems analysis, or assessing a part changing over time. In this case, a metal 3D part was scanned in different stages, removing the support structure from the 3D print. Now, the main difference between a GOM Inspect project and a stage project, where we do our statistical process control, is this bar down the bottom of the screen. So this is the separate scan datas divided up into individual projects, but this still works within the same GOM Inspect project. What this means is, if I create anything in one of these stages, it automatically gets updated to all of the others. Now, using our surface comparison, like we did before, we can assess the deviation between the scan data and the CAD model at the different stages. And what we can see is how that deviation is changing between the scan data, between the removal of the support structure. Now, another nice tool for this application is surface comparison on stage. So rather than using the CAD model, in this case we're using the first set of scan data as our benchmark, and it's inspecting the scan data of the subsequent scans back to that first stage. So what this really clearly shows is where the deviation is occurring when all of the support structure is removed back to that first stage. Using our deviation labels, we can get a really good understanding of the deviations in these exact points. Now, how this could be used is potentially analysing this deviation and applying this back to our original CAD model to adjust our print and ensure that we're getting a better quality part at the end of the print cycle.
So here we've got another stage project. So we can identify it as a stage project because there's a few new things in the 3D view. First, we've got this table down the bottom here, and this shows us our 25 scans. So what we've got is 25 scans. In this case, it was scans of the same part captured using a slightly older generation GOM scanner, which is the GOM triple scan. So we can see that table. What we can also see is a new alignments tab in the top right hand corner. So we've got original alignment, which is how it's aligned to the CAD model, and we've also got this new pre-alignment. So what this is our rigid body motion compensation. So essentially what we're doing there is aligning the 25 scans to each other. So each of those sets of scan data to each other as a best fit. So that's come up in our alignments tab in our Explorer view on the left hand side as well. So what we can do is start doing our inspection. So we've got our surface comparison. So if we change this to our standard 8 color tolerance that we've been using before, and again we can inspect every single point on this part. And what we're doing here is inspecting each of those individual scan data back to the CAD model. Anything blue means the scan data is low to the CAD model. Anything yellow or red means the scan data is high to the CAD model. The other thing we can do is our surface comparison on stage, which is right here. So that surface comparison is, instead of inspecting back to the CAD model, we're inspecting back to the scan data. So if we look at this is stage 1. And we're using this as our pseudo-nominal. We can see that because it's completely green, and then every other stage will update as we move through. So this is inspecting that set of scan data, so in this case, scan data set 9, back to scan data set 1, and where it's high or low compared to that scan data rather than the CAD model. The other thing we can do is maybe change this legend to a range-based legend, and that shows the range of deviations across our 25 scans. Again, this is comparing that scan data to itself rather than to the CAD model. So the other thing we can do here is maybe do some feature-based inspection. So for example, we've got these two features right here, and we want to create a distance check between those two. Now I've actually already created those features. So we can look down in the feature tree here. We've got our cones. So we've got cone 1 and cone 2. Now again, what we can do is look at cone 1, and we can do restore point selection to see which feature, which surfaces we use to create that feature on the CAD model. We can also use our relate to elements in the bottom left hand corner to see where that actual fitting cone is. So on the scan data, we can bring up our scan data, and again we can use a restore point selection to see what points have been used to fit that cone. Just make sure that the selection's been done correctly, it hasn't over selected into the radius or onto a different feature, different surface. We can also use our edit creation parameters icon to see what kind of filtering has been applied to this. Now again, we can't edit any of this because we're in the free version of GOM Inspect. If we're in the professional version, we could change the filtering to whatever we needed to. If we wanted to do that in the free version, we just need to delete that element and recreate it. So we've got these two cones. We should have two associated planes, which are right here, maybe plane 2 and plane 1. And then we've got two associated points, which will be intersection points between those cones and that plane to create a point on the top here. So the next thing we need to do is create a dimension. So that's this dimension here, which is just a line, basically just a 2-point dimension just between those two intersection points. And then we can do our inspection. So the inspection here is the distance check. We can log this distance check to a direction if we want, but in this case we just do a straight distance check, and that comes out here. So this is looking at is taking a nominal directly from the CAD model, and we're looking at actual, which is the actual distance on the scan data. And as we move through our stages, that will update. Which is all well and good, but then we want to have a bit more of an understanding about how we're, our full stage, our full set of 25 scans. So we hit the middle icon on our inspect, we can change the visualization of that label. So that's right here. We've got a few different options. But if we click the trend icon down the bottom here, that brings up our trend analysis for these 25 scans. So we've got our process control and the PPPK values. We've also got the averages and the max and min values. If we look at our table, which is right here, we can go to our statistics overview tab. And this gives us the same information as on the label and a bit more information as well relating to the range and the sigma values, which you can see right here. So that can all be created in an inspection report. So if we want to just bring up that label and our CAD model, we can create our report page and maybe create this as a 3D view with table, so we can capture that additional information as well. Hit that eye icon, just move the label to somewhere that's reasonable so we can see exactly what's going on. And then that's ready for export.
Another application for stage projects would be measurement systems analysis. In this project, we have 25 individual stages, as you can see down the bottom of the screen. So this is 25 individual sets of scan data captured using the Atos 5 optical scanning system. So we're measuring this probing the sphere and artifact, which has also been inspected on CMM. So what we've done is taken the values from the CMM and applied that as the nominal, and then got a length check between the two spheres, which is our actual. So from here we can see that for this measurement we've got a bias from the scan data to the CMM of 0.1 of a micron and a range deviation across our 25 scans of 1.8 microns. So from this we can get an understanding of the repeatabilities and the potential for the GOM Atos and Atos 5 scanning systems.
Thanks, Ben. Before we conclude, Olivia will join us again and give us a brief overview of the advantages of the professional version of the software over the free version. The free version has all the inspection tools, and for one-offs it's everything you could possibly need. The difference, in a nutshell, is time, and if time is money, then the professional line software offers the ability to save plenty of it. While most of the same inspection tools are available in both, the functionality that streamlines processes when measuring multiple parts is tied to the professional version. Template inspection, updating features and entire reports in seconds, customization through scripting, network licensing, and trend analysis are all the domain of the professional license.
GOM Inspect Suite is a complete inspection software, and we don't have the time to go through every feature. Some other key features to the software include surface defect inspection, deformation analysis, digital assembly, airfoil analysis, GOM volume inspect for CT data, cluster inspection for repeating features like PCDs, scripting and user-defined inspection principles, data capture and automation, virtual clamping, and mesh editing. Please feel free to ask us any questions on these features or contact us after the webinar for more information. Here we are going through a simple workflow for getting an initial inspection of a part. This will create a surface comparison, deviation labels, inspection section, and some report pages. As you can see, this workflow is identical for both GOM Inspect and the professional version of the software. The real time saving is when we rescan the part. The workflow on the left shows how a new set of scan data can be imported into the project, replace the existing data, and update all the report with the new file. This is only available in the professional software. In the free version, all the inspection will need to be created again.
Conclusions. The software is a powerful tool, whether it be the free version or the professional. The software is developed by market leaders in the field of optical metrology, GOM of Braunschweig, Germany, now a Zeiss company. It is fast becoming an industry standard for inspection requirements across a wide range of industries, from aerospace to defense, maritime to medical, power generation to additive manufacturing. The software accepts measurement data from a variety of sources, traditional CMM, non-contact 3D scanners, and even terrestrial devices. It provides multiple alignment options, leading GD&T inspection tools, and intuitive color deviation maps, as well as traditional CMM tabular reports. It is a software package that is constantly being developed with regular releases. We at Scan-Xpress are everyday users of the technology and would welcome an opportunity to answer some questions and explore further how this technology can assist you. Please stick around for the Q&A.